Yep. Or if you want to know something about Finland, then you can also use that hour. But I can also summarize. It's cold, dark place in winter time. Oh yes, we still have, say, in top 3. It depends on the survey, but we are kind of losing it. Okay, we are in top. Okay. All right. Thanks. So, hi everybody. So my name is Antti. So the ANTTI, 2 T's. That's usually the hard part to remember. Yeah, welcome on my class, and welcome. Please take a seat. Nice to have you here. All right, so a couple of words before I start actually about myself. So I'm a principal lecturer in Helsinki, well, not anymore, Helsinki, Metropolia University of Applied Sciences, which is actually on the Helsinki metropolitan area in Finland. Yeah, yesterday when I left Finland, there was a snowstorm. Okay, so it's cold, still some cold there. But it's getting better, so we also have a nice summertime there. My history, I have been teaching electronics and embedded systems since year 2000. And before that one, I was actually a let's see, senior scientist in a company, Vaisala Corporation. So Vaisala is a manufacturer of meteorological instruments, the weather stations, weather balloon, the sensor package, and that kind of things. And for example, I noticed that the Madrid airport actually have Vaisala instrumentation on the airport. Something like 80 or 90% of European air fields, they have the Vaisala instrumentation. So it was a good company, full of engineers, you know. It's a good company. Life doesn't get much better than that, except if you go to the education field. So I'm just enjoying the my educational career now for 17th year. I have been teaching this same topic in Metropolia last time, something like 2007 or 2008. It has been a while, but yeah, well, I remember some of the things, and the nice thing about this, these are fundamentals. They don't change. They haven't changed since, say, 80s. There's some really good books have become, for example, the Malik's book. That's quite recent. But it still has the bipolar transistor, it has the field effect transistors, so the fundamentals is still there. Okay, and another thing, some of this stuff is really in use still. So last week you got the theory about the A-class amplifiers. Okay, your grandparents had the transistor radios and that kind of things. They have A-class amplifiers, which means that they also nicely warm the air when you are running it. But we will be seeing that one. So last week you covered the signal part of A-class amplifier. I noticed, okay, there's the some limitations, of course. So the output voltage cannot reach the power supply voltage, since there's always the saturation of the amplifier, the saturation voltage there, at least that much. Okay. And of course, some limitations of the current source here. There's also the minimum voltage across the current supply here. But anyways, with a nice design, well, you can have a quite nice linear amplification. Excellent. Directly to the topic. Oops, sorry, not that one. right. That one. Good. So let's take a evaluation of the required power on that circuit. So this is a classic 8-type amplifier. Now I probably should start using the old-fashioned way. So, let's do a quick analysis here. So you have input voltage. I see you are marking it that way. I usually use that's a signal source. Then just to show that they are not the real universal markings of electronic circuits. That's also a ground, a signal ground, right? And other things you may actually end up seeing this kind of ground, but that's bad. It's American. Okay, American way of marking. All right, and then you have the constant voltage supply. For what reason? That's VBE. Remember? Yeah, the bias, yes. So that's basically a bias in circuits here. Right. A constant voltage that should take care of the voltage drop in here. Right. So that's the same as VBE. And then, of course, you have the positive power supply, then the load on emitter, and then you have this current supply to minus negative power supply. Okay, good. So may I take a quick look on your notes of the last time, since it's not necessarily the same as what I'm seeing here. So last time, where did you get? Oh boy, you need help on making notes. Okay. Mm. Okay. We'll see what I can do here. Oh, and in that case, if I mess up here, you can fix it next week. All right. So, power. Okay. Which parts here consume power? Where do you see power consumed? Yeah, that of course. Load, where else? So wherever you have current and voltage drop, you have power consumption. Okay. So in transistor, right? Was it DQ? Right, on your markings. And then, what else? Go ahead, make a guess. There's still something, some. Yes. So basically, there is a voltage drop also through this current source, IEE. So that's also voltage drop, which means that there is a power. Power is consumed also on that. Okay. About the voltage drops. So, okay. Voltage is always say U times I if we are talking about a constant state, or if we want to calculate the average power of UT IT dt. Okay, those meaning, okay, power here. Any guesses? You can also pick on the last week's notes, or does it say on the screen? Yep, VCE times IC. Right. Excellent. And VCE here. Oh, sorry. Let's continue from that one. If this one is V1, which is actually or input signal, what is the voltage across the load? What was the whole idea of this emitter follower? So basically, you have one VBE here, another here, so those actually cancel each other, so you have the same voltage here. That's the whole thing, whole idea of why this works as a power amplifier. So we have the VI also here. Excellent. So now, what is VCE? How do you calculate VCE? Did you already calculate that one last week? Okay, you should know it. Very simple. It's just, plus or minus. Yeah. Okay, good. So VCC, and then you have the voltage drop, which is actually this one here minus VIT. So that's actually the voltage drop over transistor. Okay. Yep, correct. And then, how will you remember Kirchhoff's current law? Since what you need to also get is, what is the I of C? Yeah, you can see it from there, of course, but where does it come from? So that's I of C. Collector current. Collector current flows here, and then it divides into two parts. So we have current through the load, and then this constant current, IEE. I used to have better handwriting. I have been using the blackboard lately. Times IL plus IEE. IEE plus IL, which is then actually the same as that one, since IL is simply voltage over the load divided by the load. VC minus VIT. Still doing it correctly. Yes, actually, yes, on power dissipation on the times IEE plus okay. On that one, there should be out. Okay, so it's basically the output. There's input and output voltage. This is a voltage follower. So just to simplify, I'm just putting that one like that. So basically, I should have used the V output T, but that's quite safe to say when you have correctly designed A-class amplifier that this actually is a good voltage follower. Okay, let's see. So the signal, if we have a sinusoid signal, so that's the first two pictures there show the situation with sinusoid signal for one period. So there's an amplitude A, and then there's the output is about the same. Okay, how about the in reality? What is the collector current? So collector current is depending on the time, okay? And there's a bias of IEE. And to keep it on linear, basically then you need to make sure that you are not saturating the amplifier. Okay. And also you don't saturate the current source, so to speak. So this current source should be able to draw enough of current from the load so that it supplies almost that V minus VCC voltage drop. Okay, but almost, not totally. If you try to get more current, then you basically start saturating on the current side, or the bias is wrong. And then, of course, if you try to have too big signal larger than the VCC, then you are saturating on the top. Saturation is not good. It causes the distortion, clip distortion. Okay. Yeah. And those pictures are more or less, well, these two. VCE and IC, which actually we could already start using that one to calculate what is the power here. Right. Ooh, that would be fun. Yeah, not necessarily your idea of having fun, but so the hard way, I would say almost the hardcore way, would be to use actually this one, since we have a alternating signal there. So to calculate the average power, you integrate over one full period of signal, and VCE is VCC minus VIT times IEE plus VIT divided by load dt. Okay, that's universal, whatever the signal is. All right, and then of course, if you just start calculating that constant, that is constant, that is constant. So there's only one function actually here. If that is sinusoid, you will get really nice equations that your math teachers loves to teach. But I'm not teaching math here. Okay. Or, okay, are you using MATLAB anywhere when you study? No, okay. Any symbolic math programs, MathCAD? No, okay. There are some tools also that would give you answer from that one. But, okay, you students, you should also know how to calculate simple things like this. Yeah, okay, with a sinusoid. I'm not asking you to do it, but anyways, that's the hard way of doing things. But there are also the engineering way of doing things. So basically, we can go and take a look at the balancing technique. Okay. Input and output power. Okay, so in optimal conditions, basically meaning that this is enough to drive the minimum voltage over that one, meaning almost negative saturation in there on the voltage. Okay. So balance with no power. Input power for plus. Okay, for power supplies, what is the input power with no signal? On the power supply point of view. Okay. So you didn't cover that one last week yet. Okay, equations, but okay. Let's see. Why it's 2 times R of what? Wait a minute. What is PCC? Collectors. No, it's the power supply. Okay. I got it. I think I got it. Of course. Yeah, of course I got it. So, power. Think of the power supply itself. Nothing more than power supply. So this power supply, it is actually a voltage supply, plus and minus. You can think of it as a series of batteries. That's just a reference ground here. There we have plus VCC, there we have minus VCC, and then we have a black box. That's the rest of the stuff. So that's our amplifier here. Right. What is current here? IEE. And without signal, so signal is 0, that voltage is 0. So basically it's just that kind of, let's put it looks more or less like this, but without signal we don't have current here. So IL equals 0. So we have just this current here is IEE, and that's a closed circuit with no current going out, so that must be also IEE. Right. So what is the power of the supplied by the power supply now. 2 times VCC times IEE. Okay. Excellent. And we have the IE in the ideal condition up there, so that's directly 2 times VCC squared divided by RL. Nothing fancy about that one. All right, and then thinking of the how much power do we actually have here, and how much do we have power here. So we're taking a look at the load side power balance. So we have power dissipation in here, which is simply that's VCU, that's IC, and that is IC is actually the same as IEE in this condition, without the power, signal power, or without the signal. So that one, yeah, this is getting messy. So, okay. Can you still see if I write something here? Are you sure? Even though you don't have binoculars? All right. So output power. So that's the power consumed in the amplifier circuitry. So we have fundamentally that's the load. On this condition, no signal means that the output actually is also then 0, meaning no current, meaning we have the same current IEE in both here, and of course that current source will always have just IEE. Okay, which means that the power dissipation on the transistor is simply that voltage drop, well, no current, meaning 0 volts at here. So it has VCC times IEE. Okay. Well, again, it's basically half of that one. So it's VCC squared divided by RL. Okay, I think, remember, now we don't have any signal. So this is the power consumption of this circuit without a signal. So it's a quiescent current, actually. And then we have the current source, same thing. Dissipated in current source is the same thing. Well, voltage drop is VCC, and then it has that current, which is VCC over RL. Okay. So, this is supplying power for the amplifier. So basically, whatever happens, this should be actually quite true condition. Why? This comes from one of the fundamentals of physics. Right. Energy doesn't appear from nowhere and it doesn't go nowhere. Okay, it's constant. If you summarize the energy or power on a circuit, the supply, you cannot supply more power to the circuit than it actually consumes, or you don't need more current than the amplifier actually consumes. That's quite simple. Which means, in this case, that we have divided the that power so that the half of it actually is consumed in the current source and half of it will be consumed in this the transistor. Okay, without any signal. All right, so without any signal, that doesn't sound too good to me. It looks like you turn a amplifier on. There's no sound, but it starts warming up the places. Not too green thing. Okay. Whoa. Now we should actually start integrating or do something else. We can also calculate the same things, the balance with the signal. Okay. And wait a minute, I have to think. Input power and output power. Well, the input power doesn't change. Why it doesn't really change is, well, does it actually? No, it does not. Are you sure that that's correct? Okay, I believe it. I take your word. So, okay. Yeah, it actually is. It is correct. Yeah. Since this is a balanced circuit, so basically, if you think of the average power, the key point here is the average power. So the input power. So how much you need from the power supply, you need to actually supply the same amount. It's just now, would you distribute part of that power to the load or not? But the power supply is still supplying the same amount of power. Okay, so PI. So that's the let's with signal. That's the power supply. Power supply point of view, it's still 2 times VCC squared over RL. And that transistor is just controlling how to distribute the power, if it's going to the RL or not. Okay. Then we need to take a closer look on all those 3 elements. By the way, why we are not actually taking care of this part on the power calculations? Any reasons? Any guesses for the reasons why I'm not calculating actually the use that one in the power calculations. Yep. And why it's small? Because of yes, exactly. Good. So this beta is actually, or HFE, Americans, yeah, evil. The current amplification is in order of 100, roughly. So basically, whatever current here, it's just about 1% of the collector current. So we can, for these power calculations, 1% is nothing, usually, but sometimes the one extra percent burns the transistor. Okay, not really. There's always this engineering factor should take care of. But okay, the output power. So we have power consumption in load. So 1 PL, simply. Okay, that was I'm not using the sinusoids yet. So PL, you have the input signal times the current, which is actually input signal divided by R2. And okay, let's do the math. If this one is sinusoid. With amplitude A, so now we have a sinusoidal signal. You're using sines, yes, good. My favorite is cosine. Squared divided by RL dt. That's actually something you should remember even if you are sleeping and someone wakes you up. What is the power on the sinusoid? Yeah. Or actually it's A squared divided by 2RL. Good. That's the power on load. So that's actually the power you want. Question. Quickie. So what is the maximum in theory? What is the maximum power on load now? Remember the saturation. Okay. So maximum power is maximum A without saturation, which is, you should remember that. So max of A. So what is the maximum value actually here? VCC minus VCE. Okay. So it's not exactly VCC, but okay, and that's in saturation. Okay, good. Any questions? Oh, by the way, if you have any questions, please just ask. Okay, what else do we have? Okay, we have output port 2, current source, current source, current source. And again, current source. So this part here, minus VCC. Okay, there we have the load. And that's the output voltage, or actually on the same time, it's input voltage. So basically, my question is, what is this? This voltage here. And now I should be pretty careful with the sign. Okay, for positive signal, we should have a positive. Okay, good. So VIEE equals V0T plus VCC. Yes. Yes, because think of this voltage drop here. That voltage drop is exactly plus VCC. Okay, what is left is the sum of those in that order. Okay. Actually, closed circuit. Oops. I should actually. Oh. Yeah. Sorry. That way. Yeah. 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 I always think of this from higher potential to lower potential. If you have signal, you always think of the signal as positive signals, then you don't make big mistakes. Which, for example, I did when I was in your situation of doing the electronics classes. Yeah. All right. So power there is simply, well, that one YEEE dissipated in. That one is the voltage drop was V0 plus VCC. Yes. Times IEE. What did I do wrong? Did I do anything wrong? VCC times IEE. What? TIE equals. What do you should actually now take over a little bit. So what's going on here since I'm not getting the same result as you? Hmm? Ah, yes, of course. Average power, since we have constant, yes. Yeah. Of course. That's why we should always do the integration. Not just look at the big pictures or equations. So we have 1 over t, integration 0 to t, v out plus vcc times IEE dt. Okay, constant, that's the sinusoid variable average signal over one cycle. 0. Okay. So that one becomes, just mark it like that, V0, that's the times sine of omega t dt, oops, times IEE. T plus the average of a constant. So that part is 0. Right, because of the constant current source. VCC times IEE. I got the same value. Excellent. I deserve a drink. This is water. Okay. Let's get it a little bit closer. So so now we can actually take again the power balance concept, meaning, okay, whatever you supply is consumed, or whatever you consume must be supplied. This is still in the case. So losses in transistor. So that's the transistor. We could, of course, go and evaluate that one. Okay. So there are cross terms. That actually goes off. That also goes off. And yeah, we could actually evaluate that one, or then we can use the power balance concept, which actually states as, okay, the supplied power equals the dissipated power in transistor plus dissipated power in the current source plus the dissipated power in load. And we've solved just that one. This is simple calculus. Even I can do it. Oops. With some sign errors, of course. Easier to equation, easier to make mistakes. And now we have everything there. Basically, we have the PI somewhere. Yeah, there. It's 2 times VCC divided VCC squared divided by RL. Then we have this power dissipated in the current source and on load. So what is left here is simply VCC squared divided by 2 RL minus the input voltage amplitude squared divided by 2 RL. Okay. So let's make a quick kind of does it make sense check. Without the signal, we should have the same as there. So without the signal, that goes off, amplitude is 0. We got the transistor power dissipation VCC squared divided by RL. Excellent. At least it works. Good. Ha. So what is the maximum of PL max? But we already had it. Or did we? Yeah. Okay. Maximum would be with that one. So VCC over 2RL. Okay. All right. This is a very important summary. So basically, total power in the circuit. That's what this dual power supply must must provide. So the P max here is same as what is the maximum power on load. Okay, that was about, well, that's the maximum power. Depends on the amplitude. And absolute maximum would be JPL max equals VCC squared divided by 2 RL. Actually, it's less than that because of the saturation voltage. All right, so basically that was 2 times this constant here, which means that in order to run, for example, 1 watt to your load, you must actually have a power supply that supplies 4 watts of power. Okay. And then dissipation of input power with no signal. So without the signal, with the blue one, we did it on the top part. Power transistor takes VCC over RL, and also the same amount is in current source. So the current source takes also 2 times the power that is consumed on the load. Okay. Yes. Mm-hmm. Yes. Yes, that's a design parameter to get the maximum slew on the output. Mm. Yeah, I mean at the middle. Yep, on like load curve. Mm. So one way of thinking of it is you have to have enough of current to drive this one to VC minus VCC. That's the absolute maximum signal you can actually put into this the output load. Okay. Since this one is powering the positive cycle, and this one is powering the negative cycle. That's one way of thinking it. Okay, so back to the red point. So the current source in this case here, current source is dissipating, well, that's again VCC squared over RL, which is 2 times Pmax. Yeah, current source. And then, okay, maximum power delivered to load comes from this one, which when the maximum amplitude, with the maximum amplitude, you get the, that's the maximum power, so it's 1, that's the same as the maximum power, yes, of course. And then, in this case, the power transistor actually dissipates, when you do the calculus here, it dissipates the same amount. Okay. Which means on the on maximum power consumed on the load, you are actually having same amount of the transistor consumption and double that one in the current source. Okay, so not too efficient. Efficiency is actually defined, so how much power you can get to the load from the power supply. Okay, so efficiency, new, right? The Greek letter. Okay, definitions. You know it. Excellent. All right, so it's power consumed on the load divided by the power supplied to the system. And with the simple calculations, the maximum power was just that VCC or 2RL, and then we had the total power for so was 2 times VCC or RL. So at the best case, you get only 25% of your power delivered to the load on this Class A amplifier. And of course, if you have a small signal, like zero signal, efficiency goes to 0. Well, it's just heating the air. It doesn't do amplification, but still heating the air. Okay. And yeah, and that also the transistor is consuming half of the power. This power supply, the current source is consuming the other half of the power, and then it's basically a kind of second degree polynomial there. Okay. Okay. Some summary. So basically, there are a couple of advantages on Class A amplifiers, although they are not anymore used much on the new designs, because, well, we have quite limited natural resources. We don't want to waste everything for heating the space, especially on summer months. In Finland, it doesn't matter actually, since we will be heating, 9 months a year, so it wouldn't matter. But the advantages is basically that this has one single active device, meaning one single transistor which does the amplification. Very simple design. Of course, this is also requires some transistors, but to make a constant current source, you don't need that finely tuned transistors as you need when you're doing a good linear power amplifying the transistor. Okay, and of course then it's quite nicely linear in this emitter follower condition. So basically, it has some non-linearity near to the opening and closing of the circuit. As you remember those the signal curves, these. Remember these, right? So we have non-linearity in the close to the saturation, and of course non-linearity on this field. But when you have the load curve there, basically it's quite nicely linear in between, because it's always actually well, it's half open on the on this design point. So it's half open at that point. With no signal, it's half open. All right. But some limitations. The biggest limitation is the poor efficiency. Only 25% max. And then the power supply also needs to deliver very high power, 4 times the power of the maximum what you put on the load. Think of now let's see, the area of when the transistor amplifiers came into the music industry. You know, you can still see there are the Marshall tube amplifiers, big bulky things with glowing elements, tubes. Compared to tubes, this 25% is already 10 times better. So, you know, the 100 watts of audio power in Marshall guitar amplifier takes about 1 kilowatt of current. The power all the time. So it's a heater. It's a space heater. Okay. So if you compare to that one, this was already advanced. So, and also the linearity and that kind of things. But anyways, so in that era in 70s, somewhere in 70s, 80s, this was a huge step for the mankind. But not anymore. 4 times power and still not, you know, even if it's just turned on. That's not a good, really, sustainable thinking there. Yeah, and the great losses mean also you need to take care of the thermal design. All right, 100 watts in your load, meaning you need to basically prepare for 200 watt dissipation in transistor and the current source. 200 watts, meaning big the cooling elements. I actually had I think it was class A amplifier, old Yamaha transistor, the amplifier for my guitar, 100 watts, and it was quite hot. On the back side, it has a big grill of the cooling elements, and then also it has a grill there, so it does airflow, conductive airflow all the time. It was a nice amplifier though. But I would like to have the Marshall tube amplifier instead. And you know, I tried to run it at the maximum efficiency, meaning, you know, all the way up. Okay, good. Good. So yeah, the best is to assemble transistor is working at maximum load. Yes. And yeah. Oh. All right. So maximum design factor in power state is maximum power delivered to load Pmax. Okay, but you still need to basically do the calculation so that the transistor will survive the so basically the bad conditions, the worst case conditions. Okay, did we have a? Oh, that was the exercise. So the worst case. So when does the transistor actually deliver the worst case scenario? Think of the transistor now. Only the transistor, since the power supply, the current source always have the same power. Only the transistor. Worst case. When is the worst case? I leave that to your home assignment. That's a good question for the exam. Worst case for the transistor. Okay. Yeah. Yeah, of course. Yeah. When the transistor consumes the maximum amount of power it actually does. Saturation is not actually bad. It's maximum current, yes, but it's also minimum voltage over the transistor. So you need to actually calculate where you have the maximum of current times voltage. So that's the key. So we have that integral there. And, well, not really integral, since this is basically the worst things happen on steady state. So that you keep the transistor at the maximum power consumption all the time. So thinking of this one so that the signal is not a variable but a constant. Okay. So everything on that one would be constant. Yes, VCC times IE okay plus VC plus, yes, of course, plus times VI, still a variable but a constant value variable, divided by RL, minus VI IE minus, it's the minus. Where did I get minus? Oh, cross terms and yeah, correct. VI squared divided by RL. And now the worst case for that one with a variable VI. That looks like a second degree equation to me. So it's a polynomial of VI, right? So that one actually depends on VI. And how to find the maximum or the minimum. It's either maximum or minimum derivative, right? No, partial differentiation of so PD Q max dVi equals 0 will get you the either worst case or best case scenario. Since you don't necessarily know from this one, it's well, you can, but but actually the can be either this way or that way. Or which way it actually is. Okay, is it the curve like that or curve like this? Which one? You can see it from the equation already. All right, how about this one? Minus something. So actually it will be a curve like that, which means that differentiating it on a function of dvi. Okay, vi. You get the maximum power dissipation on the transistor. No magic, just calculus. It's called engineering. Okay, this would be a perfect time to have a short break if you want to have, say, 5 to 10 minutes. Don't go smoking, it kills you, but 5 minutes. 5 minutes, good. Okay, break, 5 minutes.
That's a nice